We've been talking a lot about linear and quadratic approximations, and I have this example for you. So I want you to find the linear approximation for x values near 0 of this function here, e to the negative 3x over the square root of 1 plus x. So pause the video and work on this for a little bit. All right, assuming that you've given it a try, let's just remind ourselves what the formula for a linear approximation is for x values near 0. So we say for x values near 0, f of x is going to be approximately f of 0 plus f prime of 0 times x. So that's what we have for a linear approximation formula. And all we need to do to find the linear approximation of this function up here is to just find what f of 0 is and what the derivative evaluated at 0 is. So let's do that. Let's find f of 0. So let's find f of 0 first. Plugging in 0 to our function, we have e to the 0 power in our numerator, and then the denominator, square root of 1. So we find this to just be 1. And now to take the derivative, you know what? Personally, I like using the product rule when I can. So I'm going to rewrite this function as a product. So we have e to the negative 3x, and then we have 1 plus x to the negative 1/2 power. And then differentiating here, we have our derivative function to be, under the product rule, we're going to use the chain rule on this first term here. So this becomes negative 3 times e to the negative 3x power. And then we keep 1 plus x to the negative 1/2 power. And then plus e to the negative 3x power. Derivative of 1 plus x to the negative 1/2 power. You're going to use some of the power rule and chain rule, but it's going to come out to negative 1/2 times 1 plus x to the negative 3/2 power. And then a derivative of the inside is just 1. So this is what we have for our derivative function. And now we don't need to simplify this. We just need to evaluate it at 0. So let's evaluate it at 0. We get negative 3 times 1 plus we have 1 times negative 1/2 and then times 1. So that's what we have. And then let's add up these terms here and see what we get. So we have negative 3 and then minus 1/2. And this comes out to negative 7/2. So this is negative 7/2. So now we have everything we need to construct a linear approximation. So let's come back up here and fill in what we found. So let's fill in what we found. F of 0 we said was 1, and then f prime of 0 is negative 7/2. So negative 7/2, and then times x. So that's our linear approximation, and we could use this to approximate values of our function for x values near 0. Now I just want to ask, okay, could we view this function in a little different light? Is there another way to calculate a linear approximation for this function here? Well, in taking the derivative, we are taking the derivative as a product of two functions, and we could view this function as a product of two functions. So if we were to rewrite it like what we did with the derivative, we could say that this is equal to e to the negative 3x, and then we can call that g of x if we want. And then we can multiply it by 1 plus x to the negative 1/2 power. And we can call this h of x. So we can view this function as a product of two functions. And why would this help us? Well, here's an interesting thought. What if we knew the linear approximation of just e to the negative 3x for x values near 0? And then similarly, what if we knew the linear approximation for 1 plus x to the negative 1/2 power? If we knew both of those linear approximations and multiplied them together, would that give us the same answer? That is an interesting thing that we want to find out. So let's do that. Because in the last video, we found what? We were looking at quadratic approximations. But again, quadratic approximation formula has the linear approximation in the quadratic approximation formula. So we found the quadratic approximations of e to the x and 1 plus x to the rth power in the last video. But we just want the linear approximations of these guys. So e to the x, we found that to be approximately 1 plus x. And again, this is for x values near 0. And then 1 plus x to the rth power. In the last video, we said that this is approximately 1 plus rx. So now, how do we get from here to what we have over here? Well, wherever we see an x, we're going to replace with a negative 3x. And then wherever we see an r, we're going to replace with a negative 1/2. So rewriting these, we can find our linear approximations for e to the negative 3x. And this is going to be approximately 1 minus 3x. Okay. And then 1 plus x to the negative 1/2 power now is approximately 1 minus 1/2 times x. So those are our two linear approximations. And now we were interested, okay, what if we were to multiply these together? What would happen? So we're multiplying our linear approximations, g of x times h of x. And we're going to find this to be, maybe I'll switch to, well, maybe in a little bit, we'll switch colors. So we're going to multiply 1 minus 3x times 1 minus 1/2 x. So multiplying these guys out, what do we get? This is approximately, I'll switch to pink now. We're going to have 1 minus 3x minus 1/2 x, and then plus 3/2 x squared. So that's what we get. And again, these are the linear approximations multiplied together. And we want a linear approximation. So that means we're going to toss out this quadratic term here. We're going to toss out that quadratic term because we just want a linear approximation. So we should be left with a constant and some linear terms. So doing this, and what is negative 3 minus 1/2? Well, we find this to be 1 minus 7/2 x. And you can see that this right here is exactly the same as what we got over here using the linear approximation formula. So you can see that at least for this example, that when we multiply these individual linear approximations together, we get the same answer as if we were using the linear approximation formula. And in the next video, I want to prove that this is the case in general, that you can do this. And really what this is working us up to is, okay, if you were asked to solve this problem, I myself would probably go with this method over here of just using and applying the linear approximation formula, because finding the first derivative of most functions is pretty easy. But what becomes more difficult and what I want us to start to work towards is, does this property over here where we can multiply approximations to one another, does this property apply for quadratic approximations maybe? That's what we want to work towards, because finding second derivatives of functions can be pretty tough. Like this one here, trying to find a second derivative would get a little hairy. So that's what I want you to hold in the back of your mind. And in the next video, we'll prove this out in general.